Okay, thank you, David, for the introduction. Hello, everyone. Welcome to this week's CNS Masterclass seminar. Today, we'll be focusing on X-ray Photoemission Spectroscopy, also known as XPS. I'll first go into a brief introduction about XPS. Then I'll go into some detail about its instrumentation, XPS spectral data analysis, and a few applications. The goal of this seminar would be give you a clear idea how XPS works and understand what it can do and what it cannot do. So what is XPS? XPS is also known as ESCA, that stands for electron spectroscopy for chemical analysis. So it's basically a non-destructive chemical analysis technique. For chemical analysis, what we're going to do will be we're going to scattering a beam of incident elementary particle onto your sample surface. And by measuring the interaction of the elementary particle with your sample, also all the secondary particle from your sample, we can try to answer a few questions, such as what is the elemental and chemical composition on your surface, and what is the structural arrangement of the surface atoms, and what are the electronic properties of the surface. By answering this question, we can generate some kind of quantification information about your surface. So typically, the sampling depth for XPS measurement is about 10 nanometers from your sample. So from the picture right here, you can see that's the only region we're going to detect the signal from your sample. That's why XPS is being considered as a surface chemical analysis tool. So what is surface analysis and why do we care about our sample surface? So all solid material interacting with the surrounding through the surface. In fact, one of the striking features of the modern nanotechnology is the important role of the surface and its near surface region of the material. So for surface analysis, basically we can try to categorize into two parts, the physical analysis and chemical analysis. For the physical analysis, it's mostly based on some kind of imaging techniques such as SEM, FM to look for surface structure and morphology. And we can also do some mechanical testing to understanding the physical property of your sample surface. For today, we'll be focusing on chemical analysis. So by taking the result of both physical and chemical analysis, we can study your surface corrosion, surface adhesion, wettability, coating, chemical activity, even some biocompatibility and contamination. So for surface analysis, what we're doing will be we only studying the outermost layer of your material, which usually is kind of about 10 nanometer. So for a picture on the screen here, for true surface analysis, the only region we're looking for is only the top 10 nanometer of your sample. Anything below this region in the next 1 micron, we call it below surface region. And for this region, we can't detect signal from XPS. So you need to use some other techniques such as EDS, which had already gone through by my colleague Jules during our second master class. Anything further down in the bulk material region need to be using some kind of optical spectroscopy such as Raman and FTIR, which had already been gone through by my colleague Arthur during our first master class. And one of the most important requirements for doing surface analysis will be the measurement need to be very, very sensitive. That's why we can detect the signal you need above the noise level. So since we're only focusing on surface today, so we need to know a little bit about our sample surface. For ideal XPS measurement sample, the sample we're looking for should be looking for something looks like the top left-hand corner right here. That's an ideal surface, which means the surface is ultra flat with zero contamination. But in reality, most of practical systems do have some sort of contamination on your sample surface, shown as a top right-hand corner here with a white layer. So this contamination can be anything, but the most common contamination on your sample surface will be just some kind of hydrocarbon contamination. If you're building some device or doing some thin film coating, making some kind of microstructure on your sample surface, when you do your measurement on different regions, you might have some kind of shadowing or edge enhancement effect. And if your sample is kind of lateral inhomogeneous, then you might going to get different signal from different regions of your surface. So for instance, the intensity of the XPS signal will vary according to its crystal orientation. And lastly, for most of the sample, people working on some polymer sample or even some biological sample, then the surface of the sample will be quite rough. And for very rough surface, you're going to get very noisy data comparing to the ultra flat surface. So that's why before you do the measurement, you also want to make sure your sample is kind of compatible with the XPS machine, and which we'll go talk more about it later. So here's a brief history about XPS development. So the main principle behind the XPS measurement is photoelectric effect, and that was first observed by the German scientist Heinrich Hertz back in the 19th century. Then Albert Einstein wrote a paper in 1905 to describe this phenomenon and award him the Nobel Prizes in Physics in 1921. The first paper published using XPS doesn't happen for chemical analysis doesn't happen until 1950. And in the next decade, Swedish scientist Kai Sabon, he had been working on developing a fully functional XPS system, and that also awarded him the Nobel Prizes in Physics in 1981. Since then, multiple commercial vendors have been developing the XPS system, and with the engineering improvement, including data interpretation in the last couple of years, now XPS has become a very mature and established chemical analysis tool. In fact, XPS is the most common surface chemical analysis tool. So that's just a brief introduction. Now we can start to dive into the ocean of XPS. So as I mentioned earlier, the main principle behind the XPS measurement was performing the photoelectric process. So we're going to spend a couple minutes to learn what is the photoelectric process. Here we're going to use a more simple atomic model to describe this process. So what we are going to do will be, for the atomic model, the electron is kind of circulating around the nucleus, and each orbital we label with some kind of X-ray notation with the inner shell called a K shell, L shell, and so on. So during the photoelectric process, what we are going to do will be we're going to shine your atom with some kind of incident of photon. So for the XPS, we are going to use some kind of mono-energetic X-ray, and it's going to knock out one of the electrons from your atom. So the whole process can be easily written in this formula right here, where the atom of A plus some X-ray energy H nu will give you an ionized atom plus the electron coming out from the atom. During the XPS, we can measure the energy of this outgoing electron as the kinetic energy. So the formula is shown down here. So kinetic energy of this outgoing electron will be roughly equal to the X-ray energy H nu minus the binding energy of the electron that's already sitting in the original orbital right here. For the XPS measurement, the typical X-ray energy we need to use is somewhere between 1 to 10 kilo electron volt. But instead of using the atomic model like this guy here, most of the time for XPS, we will be also using the energy band structure, where the electron is kind of putting in each different energy level, starting from 1s all the way up to the valence band. So you can see right now we are trying to put each energy level using the spectroscopy notation. The Fermi level between your valence band and conduction band is just the energy of the highest occupied level at the absolute zero. And each level we try to measure in the binding energy. So the binding energy is the energy referring to the Fermi level. So earlier I mentioned the machine only measuring the kinetic energy of the electron. So how do we measure the binding energy? And I'll come to my next slide. So yeah, this slide just let me show you, we still have the same process, and the electron will be leaving the atom and going beyond the vacuum level here. So to measure the binding energy of our sample, we can try to draw a schematic of the reference energy level and try to physically align to our sample and our instrument. So the picture on top here, the orange color is our sample. So assuming we are creating the photoelectric process, the electron will be leaving our sample and going straight into the spectrometer. And when the sample is inside the system, the surface of our sample will be in electrical contact with the spectrometer. That's why you can see the Fermi level for both parties, the sample and the spectrometer, are in the same level. So by knowing they are in the same level, and we want to measure the binding energy of our sample, what we're going to do will be we'll measure the kinetic energy from the spectrometer. And we're also going to know the spectrometer work function. This guy is a known parameter from the machine. So the binding energy of the electron that's already sitting in our sample can easily calculate using the X-ray energy H nu minus the kinetic energy of the electron we measure, and minus the machine parameter, the spectrometer of the work function. So that's how we calculate the binding energy for a conducting sample. If we switch over to an insulating sample, now the things looks slightly different. So because the sample is non-conductive, when the electron is leaving our sample surface, the surface become positively charged, and because they are non-conducting, so there's not enough electron coming from the ground region to replenish all those holes. So what happens will be the Fermi level of our sample is no longer in the same level as the spectrometer. So what happens will be there's an additional charging energy built on the surface. So that's why when we try to do calculation for the binding energy again, we still take the X-ray energy H nu minus the kinetic energy of the electron we measure, and also minus the spectrometer Wall function. But now we also need to include this charging energy term. So this energy is not predictable, and it's kind of vary according to your sample condition, also your vacuum condition. That's why you need to find a way to do some compensation. Otherwise, the binding energy you measure from the insulating sample is not accurate. So we'll talk more about this charging energy later. But for now, just be aware when you're measuring the sample on an insulating sample, your binding energy might not be accurate. So let's now go into some nuts and bolts of the XPS instrumentation. Here is a full schematic for the XPS system. Different vendor might have different configuration, but the main architecture and some major components should be pretty much the same. So from the picture on the screen here, you can see we do have X-ray gun sitting down here, and it will generate some X-ray showing as some kind of cyan light path. The X-ray will go through some monochromator and eventually will be landing on our sample right here. So once we have some signal coming out from our sample, the electron will be entering some lens stage and going into the hemispherical analyzer.
Rocket launch system sent a car into space, launched satellites into orbit, and now a partnership with NASA means it's the first.
And it will go into a detector.
Take humans into orbit and to the International Space Station.
And inside the vacuum chamber, usually we also have an ion gun and a flood gun. So everything you're seeing on this screen actually is housed in some kind of ultra-high vacuum chamber. So why do we need ultra-high vacuum chamber for XPS measurement? And by the way, what's ultra-high vacuum chamber? So here is a table with different degree of vacuum and with its corresponding pressure range. For ultra-high vacuum chamber, also known as UHV, the pressure range is kind of between 10 to the power minus 8 to 10 to the power minus 11 torr. Anything below this range is does not consider as a UHV chamber. So UHV is essential for surface analysis measurement. By simply do the measurement in a much lower vacuum, such as a high vacuum range right here, it's quite easy to form a monolayer of gas absorbing on your sample surface in just a couple of seconds. And also by doing the measurement in a much lower vacuum range, your data mostly will look very noisy and have very high background signal. So for UHV chamber, usually we'll be using some kind of turbo pump and ion pump to generate this kind of UHV environment. It will help to removing some absorbing gases on your sample and also try to eliminate some contamination. And most importantly, it will help to increase the mean free path for all the particles we'll be dealing with during the XPS measurement. Just for a side note, there's another type XPS called near ambient pressure XPS machine. It's kind of slightly different from what we're talking about. But this type of XPS machine has some good potential to producing some interesting study of liquid and solid surface, especially in areas such as atmospheric environment and catalysis science. But just be aware, such systems usually have much worse sensitivity compared to an equivalent UHV instrument. So that's not something we're going to talk about today, but just for your side note, there's another type XPS in the market called near ambient pressure XPS machine. So now we'll come to our first major component inside our XPS machine. That will be our X-ray source. So in a laboratory machine like what we have here, we are not going to generate X-ray using some synchrotron, but what we're going to do will be we are going to apply some high voltage across some tungsten filament. So the picture on the right here, you can see we are going to apply some high voltage on this tungsten filament. The voltage usually we're applying is kind of between 10 to 20 kilovolt. And at the tip of the tungsten filament, we're going to generate some kind of terminating electron, which will be flying in high speed in vacuum chamber and bombarding to a piece of target. When the electron bombarding on a target, the sudden deceleration of the electron will generate some soft X-ray, a lot of heating, and some secondary electron. And the soft X-ray is what we're going to use for the XPS measurement. There are quite a few different candidates for the target material. But nowadays, the most common material for the XPS measurement will be either aluminum and magnesium. These two materials have been chosen because they have a high enough X-ray energy and they have very narrow X-ray line width. The narrower the line width for X-ray line, the better resolution you're going to achieve. That's why based on this table here, you can see the magnesium target actually can give you slightly better resolution data. However, we can put more power density to aluminum target. That's why aluminum target can give you a deeper depth on analysis and also give you higher X-ray output. So aluminum target is mostly found from most of XPS machine. But the soft X-ray we generated from this X-ray gun is still not usable for XPS purpose. The raw X-ray coming out from this window actually we consider as some kind of dirty X-ray. So we need to go to some kind of monochromator to do some filtering. So the filter we're going to use is just some kind of Johann Benz quartz crystal plane and use it as some kind of diffraction lattice. The way we design the diffraction lattice is quite simple. We can use a Bragg equation where n is the diffraction order, d is the distance between the crystal plane, and the delta is the angle of diffraction. And the lambda is just the wavelength of our incident X-ray. So by going through the X-ray through the monochromator, we can try to remove the Browns-Strong radiation and narrow X-ray line width further down by about 0.3 eV. We can remove the X-ray satellite, and also, most importantly, we can focus in the X-ray beam to a desirable X-ray spot size. Now we have X-ray ready, and our sample generates some signal. So the signal, the electron will go in straight into the analyzer. For XPS measurement, so you can see the analyzer actually have a 2-stage. Our sample is sitting down here. So once we have some electron coming out from our sample surface, you will go into the first stage, which is the focusing lens stage. The lens will help to control the acceptance angle to maximize the correction angle to ensure high transmission and sensitivity. Then the electron will enter into a second stage, which is called hemispherical sector. In the second stage, the electron will be accelerated or retarded by some user-defined energy, also known as a pulse energy. This pulse energy is very important. You will affect both the transmission of the analyzer and also your analyzer resolution. So the electron will be spread out in the second stage here, according to the formula down here, where small e is just the charge of each electron. Delta V is the potential difference between the hemispheres, and R1 and R2 are just the physical radius distance for the chamber here. So usually for the XPS measurement, we'll be using some kind of constant analyzer energy mode, which means you'll have a constant pulse energy with a constant resolution throughout your entire spectrum. And usually the analyzer resolution is typically considered as about 1% of the pulse energy you set. So that's why the lower the pulse energy you use, the higher the resolution, the data you're going to achieve. Finally, once we have the data spread, the electron spread out, it will be detected by the detector. For XPS measurement, the detector it just means some kind of electron multiplier to count the arriving individual electrons. For a single channel electron multiplier, we call it channel electron multiplier, also known as channeltron. And for channel, there's another type multiplier called channel plate, which is kind of like a small disk, as a picture shown here, with an array of small holes on the disk. Usually, for XPS measurement, we'll be using some channel plate. But this kind of channel plate can help to detect the data in 2-dimensional. For each individual channel, the electron will be coming in and creates a series of multiplication inside the channel, and eventually you will land into a resistive anode charge division device and to a preamplifier to amplify the signal. Usually for XPS measurement, the channel plate has about 128 detectors, so that's 128 channel inside these sticks. So the next major component you'll be seeing most of the time on the XPS machine is called ARGON. Earlier I mentioned when we do some XPS measurement on the insulating sample, we have an additional charging energy built on your sample surface. That's why if you're working on any sample such as powder, polymer, or even some biological sample, any sample that doesn't conduct well, we might need to use a ARGON to do some kind of charge compensation. So the picture on the right is kind of a cartoon for ARGON. What this guy is doing will be, the first thing will be, you will try to backfill your chamber with some argon gas. So you can see there's a gas in there right here. So you will fill the entire chamber with some kind of argon gas. Then the electron gun on top here will be using some kind of low energy electrons and ions to neutralize your entire sample surface down here. The energy for the electron and ion are pretty low. Usually it's kind of between 0 to 5 eV. So with such low energy, most of the time it won't damage your sample surface. And here I'm going to show you data I took in the past. So the data is coming from a piece of Teflon. So there are 2 spectrons on this data set. So, and they are coming from the same sample and same spot. The only difference will be for one spectron, the cyan spectron, I try to turn on the ARGON, and for the magenta spectron, I try to turn off the ARGON. So you can clearly see the difference. When the ARGON is turned on, we can define each P very nicely. For instance, the small P right here, that's a carbon 1sp. And for the huge P right here, that's a fluorine 1sp. But once we shut down the ARGON, now you can see the intensity for each P have been decreased significantly. And also, if you try to zoom in into the middle of the magenta spectrum right here, you can see a small peak right here that actually corresponds to our original carbon peak sitting right here. So you can see once we have some charging issue happening on our sample surface, the peak have been shifting by a couple of hundred EV from this case. And also for each peak, the peak have been broadening quite a lot, and that will also degrading the chemical specificity. So that's why for this kind of magenta spectrum, it's very hard for us to determine any elemental information and any chemical information. So the fluorocarbon is kind of pretty critical for any sample that doesn't conduct well. The last major component you will be seeing most of the time on the XPS machine is a sputtering gun. So the sputtering gun we're talking about here is doing some damage on your sample and doing some etching. So that's why even though we say XPS measurement is some kind of non-destructive chemical analysis technique, but once you involving the sputtering gun in your measurement, you are doing some kind of destructive measurement. So for XPS measurement, you only want to do using sputtering gun for two purposes. One will be for surface cleaning, and the other will be depth profiling. So since we do only care about our sample surface, so we also care a lot about how clean is our sample surface. So sometimes if your sample is kind of thick enough and you can tolerate to do some etching on your top layer, and you don't care about the surface chemistry, you can go ahead and do some surface cleaning to remove the top layer and do the measurement on a clean area. As for depth profiling, it means you want to see how your material change in the Z direction. So you want to see how your material change from the top layer over to somewhere inside your material. For most of modern XPS machine, the sputtering gun will have a dual mode ion etching type. And most of the time, the etching will be using some kind of inner gas, and argon is the most common gas. So we just need to do some kind of physical bombardment on your sample. And two-type etching will be either monatomic ion source or cluster ion source. For monatomic ion source, you can see from the picture on the left here, there's a single blue ion coming down to your sample, and it will penetrate through quite deep into the surface. The ion have very high energy, that's why it will also damage your surface chemistry a lot. On the other hand, we have another type of etching called cluster ion, and this guy, you can try to picture this guy as some kind of huge bucketball. So the huge bucketball will come down to your sample surface. Each atom inside the bucketball will have much lower energy, so you can minimizing your surface penetration, also reducing the damage on your surface chemistry. But with such a low energy atom, that's why the etch rate will also be very slow. That's why most of the time we'll be saying if you're working on some kind of organic material, some like carbon-based material, we'll be using cluster ion to do the etching, so you can still preserve the chemistry on your sample surface. But if you want to etch into some inorganic material, but you definitely need to use a monatomic ion to do the etching. So that's pretty much everything about the instrumentation. Now we can start to talk about the data that's been spit out from the XPS system. Before let's talk about data, let's spend another couple of minutes to talk about data correction during the XPS measurement. Nowadays, most of our XPS machine is quite easy to operate, but we are doing surface analysis, so that's why we still need to plan ahead before you start working on your sample. So for the XPS machine, the raw data you're going to receive from the XPS machine is either surface spectrum or the high resolution spectrum. That's the only two data you're going to receive from the XPS machine. Any quantification information, any like image information is all some kind of post data processing. So the raw data is just either surface scan or high resolution scan. And for most of XPS machine, there's some kind of sample size limitation. So you might want to measure to know what's the maximum size you can handle for the machine you are planning to use. And also you want to make sure the sample you're going to work on should be vacuum compatible. We're going to do all the measurement in some kind of ultra high vacuum environment. So the sample need to be vacuum compatible. And also here I mentioned the stage height adjustment. So during the XPS measurement, we do care a lot about the height of your top sample surface. So we want to make sure the your sample surface should be within the focal length underneath the X-ray gun. Anything out of focus from the focal length, you're going to get very different XPS signal. And that's why we definitely do care about the top surface of your sample. And for most of XPS machine, there's multiple stage you can use to do different purpose. For instance, the picture on the left here is just a standard stage we have in our lab. And next to it is some kind of tilting stage. And the one next to it is some kind of electrical biasing stage. And very last one, the one on the right here is some kind of vacuum transfer stage. So that's why you want to plan ahead before you're loading the sample on the stage to decide what you want to do during your XPS measurement and what kind of signal you want to get from your sample. During the measurement, you also want to decide, are you going to do some kind of point analysis, or do you want to do a line analysis, which means you want to see how your material change in the 1D direction, or do you want to do some mapping and see how your material change in a 2D direction? And lastly, you also want to decide, do you want to do some sputtering, which means it's some kind of destructive measurement by involving the sputtering gun, or do you simply just want to see how your materials change in the Z direction? Here, the table just means some kind of standard parameter we've been using in our lab. So again, the pass energy is one of the most important parameters during the XPS measurement. For survey, we are typically using 200 eV, but when you do the high resolution scan, we'll be lowering the pass energy to a 50 eV. You can definitely lower this number to like 20, 10 eV to acquire some kind of ultimate energy resolution. But just be aware the natural line width of each photoelectron peak is combined with the width of the X-ray source. That's why you might have very little benefit to using very, very low pass energy such as 1 or 2 eV. And the ratio parameter just means helping to improve the signal to noise ratio. So another side note will be, if you're planning to try to do some quantification analysis or do some quantification comparison from different spectrum, all the spectrum should have using the same pass energy, so the data will be comparable. Now we'll start to looking for our first data type, the survey scan. So usually the data you're going to receive from XPS measurement is usually kind of displayed in some kind of intensity, also known as some kind of electron yield, versus the energy. The energy can be binding energy or kinetic energy, and you can easily switch over during your post-data processing. So the spectrum you are seeing on the screen is some kind of raw data from the machine, and the data is coming from my sample is a 10% palladium in some kind of carbon catalyst. Once you receive this kind of survey spectrum, you can perform both qualitative and quantitative elemental analysis. So for the qualitative analysis, what we're going to do will be, first we're going to do some peak labeling to know which peak belongs to which element. So now you can see we do a small chlorine signal down here, and we have a huge carbon signal down here. And we have a couple palladium signal, like palladium 3D right here and palladium 3P right here. Any element with a label called KLL or MNN sitting behind means this guy actually is the OJ signal. So we are not doing OJ measurement here. There's some kind of dedicated OJ instrument somewhere, but we are not doing OJ measurement here. But our XPS data can still pick up some OJ signal. We'll talk more about OJ later. But just for now, for the XPS, the photoelectron peak, we'll be using some kind of spectroscopy notation to do the labeling. But for OJ signal, we'll be using X-ray notation to do a labeling. So once you have a peak label and knowing which peak belongs to which element, we can do some kind of quantitative analysis. So now based on this data, and I have almost like 92% of carbon and almost like 1.2% of palladium. So the data you're seeing on the screen actually depending on a few factors. So there are three main factors that's affecting the data you receive on the screen. So the first factor will be photoionization cross-section, and the second factor will be the surface sensitivity, and the last factor is just the final state effect. And now we're going through each factor so you will know why you receive this kind of data from your sample. So the first factor is called the photoionization cross-section, also known as the probability for an electron to emit out from its electronic state. So this guy can help you to determine the relative intensity of the cold level peaks. Earlier you see from my survey scan, you can see we have two palladium signal, 3P and 3D, but they have different intensity. That all depending on our photoionization cross-section. The graph down here just means some kind of theoretical calculation done by James Schofield back in the 1970s. So what he is doing will be he try to use the X-ray mass absorption coefficient to calculate the photoemission cross-section using the aluminum K of our X-ray. In his calculation, he tried to treat the carbon C1s as 1. So you can see for the atomic number equal to 6, and we bring out here for 1s peak is equal to 1. So that's for the baseline. So that's why we call this guy as some kind of Schofield cross-section graph. So based on the graph, you can see the light element usually can give you the lower cross-section number. And for heavy element, usually you have higher tendency to have electron coming from a higher orbital shell than an inner orbital shell. So that's all based on the photoionization cross-section. The next factor that's affecting the data we receive is called the surface sensitivity, and there are two components in this part. The first component is depending on the X-ray you are using. So the X-ray we are using for our XPS measurement has an initial intensity I0, but once the X-ray entering into our material, the X-ray intensity will decrease exponentially according to the formula down here, where mu equal to the absorption coefficient, and x is the distance for the X-ray to entering into our sample. So you can see the deeper X-ray going into our sample, the intensity will decrease even more. Just a couple nanometer into our sample, usually the X-ray intensity is no longer powerful enough to knock out any electron from our sample. And the second component for the surface sensitivity for XPS data is derived from the attenuation of the photoelectron as they travel through the material. Because those low energy electrons will undergo some inelastic correction within the sample and show as a background signal. So here on the left here is a classical graph for the effective attenuation length versus electron energy. The effective attenuation, also known as an elastic mean free path. So by using aluminum K alpha X-ray, you can see our detection range is only somewhere around here with a cyan dots right here. From this inelastic mean free path graph, it exhibits a minimum for electron with a kinetic energy between 50 to 100 eV here. At low energy, the probability for the inelastic scattering decrease. That's why we can only detect a signal in this region over here. The final factor that's affecting the data we receive from XPS machine is called the final state effect. And the final state effect is the final state contribution is also known as a Rayleigh section energy. Because when we removing one electron out from our system, the entire system become unstable. So you will go through a series of Rayleigh section. And the first component for the final state effect is called the spin orbit splitting. And this guy, depending on which shell electron is coming out from your sample. So if the electron is coming out from the S shell, you're going to receive one single peak. But if the electron coming from a PDOF shell, you're going to receive double peak. So the data on the right here is a survey scan for gold surface with some mild condition of contamination. That's why you can still see some carbon right here and some oxygen right here. For both carbon and oxygen, they are coming from the 1S shell. That's why we are only one single pH, the table shown. But for the gold signal, the gold 4D signal, you can see we have gold 45 half and also gold 43 half. So the D shell do have double peak. And if you zoom into F shell, you're also going to receive two peak right here. Different region of double peak have different area ratio, and this number is quite important when we do some quantification and peak fitting for your data. And the next final state effect is called the multiplex splitting, also known as exchange splitting. And this part mostly happens when the system has an unpaired electron in the valence band. So the exchange interaction will act only between electrons with a parallel spin. The picture down here is just some example using manganese oxide, Mn2+. In the system original, we have 5 electrons in a 3D shell, and we have pair electron in a 3S shell. When we do XPS measurement, we knock out one electron from the 3S shell. The remaining electrons have a tendency to spin up or spin down. And you can observe this kind of multiplex splitting in the 2P spectrum. So the data on the right here is the 2P spectrum for the manganese. So when we do some peak fitting, you can see we can try to fit a main peak right here, but somewhere about 0.9 eV below this main peak, we also see a slight shoulder peak, and this shoulder peak is due to the multiplex splitting here. The next component for the final state effect is called a shake-up satellite, and it mostly happens when the valence electron have been excited to a higher unoccupied level. You can easily observing this kind of shake-up satellite peak on a 2P spectrum in a D-band transition metal. So the picture on the left here is just a partial periodic table with most 3D transition metal. So the disturbance of a 3D electron will give you this kind of shake-up satellite peak. The data on the right here is some kind of high resolution scanning for the copper 2P signal. So we have copper 2P 3 half and also copper 2P 1 half. Next to this 2P, we also have 2 smaller shake-up satellite peak. So you can also observe this kind of shake-up satellite peak from some bonding to anti-bonding transition, also known as a pipeline transition. And that'll be useful to confirm some kind of aromatic ring structure from some organic material. And the next component for the final state effect is called the OJ signal, also known as the OJ parameter. So earlier when we observing our survey spectrum, we say we can observing both OJ signal and XPS signal together. And now we're going to spend a couple minutes to know why we're going to pick up some OJ signal. So again, when we do some photoelectric process and removing one electron out from the system is unstable. So one of higher orbital electron is going to fill in the hole we just created. And eventually the outer shell electron is going to be leaving the atom and known as an OJ electron. We can also measure the kinetic energy of this OJ electron, which is roughly equal to the first binding energy of the first electron minus the second binding energy of second electron minus the third binding energy of the last electron. And the OJ parameter just simply usually written as some kind of symbol called alpha, and which is roughly equal to the kinetic energy of the OJ electron plus the binding energy of the co-level electron inside this atom. So why do we care about the OJ parameter? Because the OJ parameter is useful for some kind of chemical state analysis without the interference of the surface charging. So when we have some charging issue on our sample surface, usually the charging will happen more obvious from the XPS signal, but it will be less obvious from the OJ signal. That's why sometimes we can use OJ parameter to determine different chemical structure and chemical state inside your sample. And the very last component for the final state effect is called the plasmon. And that just be some quality oscillation of the surface electron and suffer some discrete energy loss in multiple of characteristic plasmon frequency. And mostly you can only see this kind of plasmon peak on some kind of ultra clean metallic surface such as a magnesium or aluminum. The data on the screen is just some kind of aluminum 2s peak and 2p peak. So next to this two main peak, also see a few tiny peak. That's a plasmon peak. And for the case of aluminum, the separation between the plasmon peak is about 15 eV. So that's all the final state effect I want to discuss today. Now we can go in and look at our second high resonance scanning. Actually, earlier you already see a couple high resonance scanning when we discussing the final state effect. And the reason we want to do some high resonance scanning for some region of your survey scan simply means we want to get better chemical state information. So the data on the screen is just a high resonance scanning for the palladium 3p signal from my earlier sample, the 10% palladium in the carbon catalyst. And based on the data on the screen here, we can do some kind of peak fitting and using some chemical state information and determine the stoichiometry information of my material. So based on this data, you can see actually I only have about 15% of pure palladium metal. The rest are just some kind of oxide material with different kind of oxidation state. So I have about 80% of PDO and about 5% of PDO2. So for people working on oxide material, usually you want to do some high resonance scanning for the metal peak instead of using the oxygen 1sp. Usually the oxygen 1sp doesn't shift too much with different kind of oxidation state. So to determine the stoichiometry information, the metal peak will be more useful. And by now you might say, then how do you generate all this atomic percentage? So for XPS data, what we're going to do will be, we're going to subtract the background signal down here and do the integration for peak area on top here. And that's why I come to my next topic about the background subtraction. So for XPS data, we have a few mathematical algorithms you can use to do some background subtraction. And the most simple background subtraction will be using a linear algorithm, which just means pick 2 points at a tangential background and draw a straight line. But we also have some kind of background subtraction called Shirley background and Toga background. Today, I won't go into detail about describe these two background subtraction. And if you're interested, you can read a 1972 paper from Shirley and also 1996 paper from Toga, and they can give you a clear idea about how this background subtraction have been derived. But just for your information, the Toga background subtraction is relying on some kind of physical model. So you will take into account some cross-section for some energy loss. That's why usually the Toga background subtraction will be slightly more accurate. But the Toga background subtraction require a minimum scanning range about 50 eV. So most of the time for high resonance scanning, such as some high resonance data, we're still using some Shirley background subtraction for the data analysis. Once we subtract background, we'll do some quantification. And to do the quantification, we need to create some model. The model for the quantification is quite simple. So we are assuming the intensity for the atom we receive from your sample is kind of sitting in a thin layer about dz thick, embedded inside your material about z distance underneath your sample surface. So that's a model we create for the quantification, and that generates this equation up here, where the first term is depending on our electron analyzer And the next two terms is relying on the photo excitation. The exponential term is the peak attenuation due to the inelastic electron scattering. And the very last term is just the effect of the angular deflection due to the elastic electron scattering. So by plugging all in the number and also the intensity we receive from the spectrum, we can generate the atomic percentage for each element that show up on your surface. Even though when we do the quantification, we are not taking into account of your background, but the background signal, also the peak shape around your photoelectron peak can give you a lot of additional information, especially if your sample has some kind of different nano structure on the surface. So the data below here are just 4 different samples. The sample are just some copper atom sitting on some kind of gold substrate. So the sample A have the copper atom sitting on the surface of the gold substrate, but sample B is sitting on one side of gold substrate. For sample C and D, the copper atom is embedded inside a gold substrate with different depth. So if you go ahead and do some high resolution scanning for the copper 2P, you can see the photoelectron peak is pretty much the same. Even the intensity for these 2P are almost the same. But once you're looking into the background signal, you can see some difference. So for sample A, where the copper atom is sitting on top, we have very few background signal down here. But for sample D, where the copper atom is embedded underneath the gold material, we have a huge background signal. So that's why the background signal can give you some additional information about where your signal coming from, and that can improve your quantification too. So earlier I mentioned we can use the XPS data to determine different stoichiometry information for the oxide material, and that's all depending on the chemical shape. Because for each photoelectron peak, it should be always sitting on the same binding energy. So by ruling out any potential charging issue, any remaining peak shifting of your signal will be just simply relying on the ionic or covalent bonding, also known as an electronegative effect. So we can look at this chemical shift by using the point charge model. So where the final binding energy you're going to receive from your data will be equal to the summation of your original reference energy plus the weight charge of the atom you're working on, which relate to the electronegativity, such as the valence change, plus the summation of the potential surrounding this atom you're working on, such as due to the reaction in the final state and the lattice change. So the rule of thumb will be, if you try to withdraw some valence electron charge from your sample surface, such as during the oxidation process, you'll be increasing your binding energy. But if you try to add in some valence electron into your system, you'll be decreasing your binding energy. The table on the right here gives you some different binding energy for the carbon material. So for carbon CC bond, usually will be sitting around somewhere around 284.8 EV. And if you try to bind a carbon with some other element like nitrogen, chlorine, fluorine, they will be changing your binding energy. And that's all about the data I want to describe today. So let's start looking for some application you can use for XPS measurement. Even though the first main type of data you're going to receive from the XPS system is the elemental information, but if your data have high enough resolution and can get a nice peak fitting, you can get some kind of molecular information. So the data on the screen are just the high resolution scanning for the carbon C1 scan and also oxygen 1s scan. So for the carbon scanning here, you can see we do have 3 peaks. The first main peak, the yellow peak, is the bonding for the carbon CC and CH bond. So for the XPS measurement, we don't have enough resolution to differentiate between CC and CH bonds. That's why they will always show up as a one single peak. But we can differentiate between a single O bond and also C double O bond. And we can tell the information we get from the spectrum and corresponding to the molecular structure of our sample. So this sample is just a PET polymer. And same thing for the oxygen. So we can differentiate between the oxygen carbon double bond and also single bond, and that also can correspond to your molecular structure for the PET polymer. That's why if you have a high resolution scanning, we can still determine some kind of molecular information about your sample. We can also use XPS data to determine some kind of thin film thickness. So the sample, the data on the screen is just some kind of silicon substrate with some kind of titanium nitride thin film coating on top. So by now you should know the intensity of each element we receive is kind of linearly corresponding to the amount of elements show up on the surface. So we put in the X-ray to our substrate, we are going to get all the signal from the silicon substrate only. But if you're going to put the X-ray to the titanium nitride thin film, you're going to receive all the signal from your titanium nitride signal. in between with different thinners, we're going to get a mixture of different intensity for silicon substrate and titanium nitride signal. So by plugging all the intensity information into some kind of two-layer model, we can easily extract out the thickness of the titanium nitride thin film we are working on. So that will be very useful if you're working on some ultra thin film and you want to know the thickness of the film. Earlier I mentioned we can use XPS machine to do some depth profiling, doing some kind of destructive measurement. And here is one example using monatomic argon ion source. So the sample is a low emissivity glass. So what's so special about this kind of glass will be you will keep your house warm during the winter time and keep your house cold during the summertime. And the trick will be we have multiple additional layer coating on top of the normal glass and do the reflection for the sunlight and so on. So the data on the left here is just some atomic percentage versus the depth. So you can see initially we do a scanning on the top surface and that only give you a signal from the silicon nitride. But doing some depth profiling and going into our sample, we can see a few different oxide material and also see some material layer as a silver right here. So using this data, we can try to study the impurity for each layer. We can also study the depth of each layer. And we can also study the interfacial region between two layers. And on the screen, I mentioned during this measurement, I actually doing some rotation on the sample. So for this measurement, it actually took quite a long period of time. So with a long period of sputtering, you can damage your surface quite a lot and the surface will become very rough. So we can try to do some rotation during sputtering to smooth out the surface, and that will help to improve the depth resolution for each layer. And the next example is some kind of also depth profiling, but now we are using argon cluster source. The sample is a piece of PET polymer with some kind of fluoropolymer coating. So this coating can help to make your PET polymer hydrophobic and have some kind of water repellent capability. The data on the left here is just still some kind of concentration over the edge time. So you can see initially we do pick up some foreign signal, and that will be a main signature for this kind of hydrophobic coating. And once we finish all the coating and going into the substrate, the PET polymer, and we determine the atomic percentage for carbon and oxygen, which is exactly the same as the concentration you're going to expect to get from this molecular structure. That's showing the cluster ion etching doesn't damage the chemistry of the PET polymer. By now, we keep saying for XPS measurement, the sampling depth is about 10 nanometer. So what happens if you say you only care about the top 5 nanometer or top 2 nanometer of your sample? For XPS, we can do some trick to just determine the signal from the very top layer. Then we'll be doing some kind of angle resolve XPS. For the normal XPS measurement, what you're going to do will be you're going to shoot in your sample with some X-ray gun and getting signal out and going into the analyzer in the 90 degrees angle. We call this angle as some kind of takeout angle. By tilting your sample surface towards X-ray gun, we can reduce the takeout angle. So you can easily determine your sampling depth using the formula down here. The sampling depth D will be roughly equal to 3 lambda. Lambda is an inelastic mean free path for the element you're working on the surface, and the delta is just a takeout angle will be changing. So this kind of angle result XPS measurement can give you very good absolute depth resolution. And that's why you come to my next example using the angle resolve XPS measurement. This guy is still a depth profiling data, but it's not a destructive depth profiling data. It's a non-destructive depth profiling data. The sample is coming from a piece of gold surface with some kind of monolayer cell assembly coating on top. We know the gold surface is pretty inert, so usually it's pretty hard to get any chemical reaction on the gold surface. But one special molecular group called thiol group can bind to the gold surface. Usually the coating is only a couple nanometer, not even more than 2 nanometer. So we can't even use a cluster ions to do the destructive depth profiling, but we can use in the tilting stage. So the data below here are 2 different kind of thiol group, and both shown as a concentration versus the depth. So by doing the depth profiling, you can going through the entire monolayer coating, then we go to a gold substrate. In case in between between the coating part and the gold substrate, we do see a small sulfur piece showing up, which can give you a clear indication that the thiol group is the sulfur is the main candidate that's binding to the gold surface. So that's why we can use this kind of angle resolve XPS measurement to get some kind of sub-nanometer chemical information within the top layer of your sample. We can also using XPS data to do some mapping. So the data on the screen are just some kind of mapping on my on the Harvard logo on my business card. So I just make card the logo and dump it to the XPS machine. So the data on the left here is just the mapping using carbon signal. So you can see based on the data here, the red color region actually have much more carbon content compared to the black and white region. And if you switch over to aluminum and oxygen mapping, now you can see the red in has much fewer aluminum and oxygen. So you can get some kind of interesting image based on your surface elemental and chemical information. So that's why some people call this image measurement as some kind of XPS imaging. But it doesn't just give you some kind of interesting image, it can also help you to study the surface homogeneity. The data on the right here is the overlay image for the three elements. So the carbon should be green, the oxygen should be blue, and the aluminum should be red. By putting all these three layers together, now you can see the red color in region become magenta, which means this region is a mixture of aluminum and oxygen. So that pretty much should be aluminum oxide right here. So the resolution for this kind of image is kind of depending on your X-ray spot size. So usually you can go down to about 10 microns for each pixel. The next application you can do will be, you can use the XPS data to do some kind of valence band data analysis. For the valence band we're talking about is doing some scanning in some low binding energy region. Usually it's kind of between 0 to 30 eV. So in this region, the photoelectron cross-section is pretty poor. So that's why usually the data is pretty noisy. So you need to do a much longer time of scanning. And in this region, you're not going to get any elemental information, but you can get some kind of chemical information. So the spectrum on the screen here are two different polymer. The magenta spectrum is coming from polyethylene, and the cyan spectrum is coming from polypropylene. From the polypropylene, we do have a CH3 bonding, which doesn't show on polyethylene. That's why you can get some kind of fingerprint from different systems for different in different polymer. The very last application you can do on the XPS machine is doing some kind of wall function measurement. Earlier, I briefly mentioned about in the sample, we have some kind of sample wall function. And what is wall function? So if you want to removing some electron out from your sample surface, you need to do some wall, and the minimum wall you need to do will be called a wall function. So the data on top here are just some normal survey scan. So usually, if you're working on some metallic sample, we are treating your Fermi level will be sitting somewhere around 0 binding energy here. And in order to do the wall function measurement, we need to know your energy for your higher energy count energy right here. But most of the time, you won't be able to observe this edge because it's being overshadowed by the spectrometer wall function, the ray spectrum here. So we can do a trick by doing some kind of electrical biasing to shift your spectrum towards right. So we're applying some kind of negative bias voltage. So for instance, if you try to apply some 34 on your sample surface, we can shift your spectrum by 30 eV towards right. Then you can start to see the edge of this spectrum. So the wall function can easily be calculated by taking the photon energy, our X-ray photon energy, minus the cutout energy of this edge. On the screen, you can see some measurement I took from some standard material. For instance, the gold wall function is about 5.32 eV, and silver and copper. And just be aware, the wall function measurement is very sensitive. It's kind of depending on our solid crystal pen, and also depending on how you pre-trip your sample before the measurement. So for all the data you're reading on the screen, actually I have been doing some kind of monatomic argon sputtering for a couple minutes before I do the measurement. That's why whenever you try to compare different wall function measurement from different experiment or different paper, make sure you also want to pay attention to how they pre-treat the sample surface before the measurement. And that's all the application I want to talk about today. So let's come back to CNS. So what do we have at CNS? Right now at CNS, we have two XPS machines, and they are both coming from Thermo Scientific. So the first machine we have is called a model called K Alpha Plus. And this guy can do everything I talk about today for the XPS measurement. And it also have a dual mode ion source, so you can do the monatomic argon ion source etching and cluster source etching. We also have a second machine called NEXSA. And this guy can do everything XPS can do, the K Alpha Plus can do. And it can also do UPS measurement, Rails measurement, and ISS measurement. So for XPS part, there's not much difference between these two machines. So they are both using some kind of monochromatic micro-focus aluminum K Alpha X-ray. And they both can handle the same size. So the maximum size they can handle for both machines is about 60 millimeter by 60 meter in X and Y direction, and about 20 millimeter in the Z direction. And since we have this NEXSA machine, so let's spend another couple minutes to learn what we have on the NEXSA. So let's recap what we have for XPS. So for XPS, we are shooting a sample with some X-ray and getting some photoelectron out from the sample surface. And for the UPS, that stands for ultraviolet photoelectron spectroscopy. So what we're doing will be, instead of using X-ray, we're shooting a sample with some kind of UV light, but we're still getting some photoelectron out from your sample surface. Then you might ask, then what's the difference between these two? So for the UV source, we are using either helium-1 or helium-2. The 1 and 2 just stand for whether the helium UV light is coming from a slightly ionized helium atom or neutral helium atom. So for helium-1 UV light, the energy is about 21.2 eV, and for helium-2 is about 40.8 eV. So you can see, comparing to X-ray we are using for XPS measurement, the UV light source is much low energy. That's why for UPS measurement, we only knock out the photoelectron from the valence band. So you won't be able to get any elemental information for UPS measurement, but you can get some very nice chemical information for UPS measurement. For ISS measurement, that stands for ion scattering spectroscopy, also known as LEIS, low energy ion scattering. So what we're doing will be, we're shooting your sample with some kind of heavy ions, and the ion will create some kind of binary correlation and scattering back to the detector after losing some energy to your surface atom. So don't get confused for the ISS measurement to the SIMS. I know last week my colleague Austin had been talking about SIMS and Atom Pro. And for SIMS, what we are monitoring for the particle is using the mass. But for ISS measurement, we are monitoring the energy of the particle. And the last measurement is called REOS. That stands for reflection electron energy loss. And this guy is kind of similar to ISS measurement, but the difference will be, instead of using heavy ion, we're using much lighter electron. So the electron will be shooting on your sample, losing some energy, and go back to the detector. And what do all these 4 techniques can do? So first of all, you can see all these 4 different techniques, we are monitoring the energy. So we are not monitoring any mass or anything. So everything we are monitoring for the particle is the energy. So for XPS, the sampling depth is about 10 nanometer. For UPS build is much lower energy, so usually it's kind of between 2 to 3 nanometer. For REOS, that depending on energy you're setting, so usually it's kind of vary between 0.9 nanometer to 5 nanometer. For ISS measurement, we are only detecting your sample on the top monolayer. So that's why ISS measurement is the most sensitive measurement we have among these 4. ISS measurement can only give you some kind of elemental information. So that's why we can use ISS measurement, try to determine some kind of thin film coverage. For instance, if you try to do some LD coating for just a couple cycle, you can try to do ISS measurement to know if your thin film is fully coverage on your sample surface. You can use REOS measurement to determine your sample band gap and also determine your hydrogen atom. So XPS is nice. It can give you all information for all elements except hydrogen and helium. That's why we can use a REOS measurement to determine the hydrogen inside your sample. And mostly you'll be using some UPS measurement for some chemical state information and also to determine some kind of electronic property of your material. Now I will go through another 2 examples from NEXSA. So the first example I want to show you will be doing some kind of hydrogen quantification. So this data below here is some raw data from the REOS spectrum. So the data is coming from different 5 different samples with different chemical structure. And what we try to do will be try to quantify the hydrogen we have from these 5 different materials. So data on the right here is a comparison between the measured hydrogen concentration to the measured hydrogen concentration. You can see from the data, they have a very close agreement between the measured data and the expected data. So that's why you can use the REOS measurement, try to quantify the hydrogen inside your material. And the very last example I want to show you will be doing some measurement on some organic LED material. The organic LED material we're talking about here is a PFO material. That's a blue light emitting material. This guy have very low turn-on voltage with very high brightness and efficiency. So the molecular structure is shown on the screen right here. The sample for the XPS measurement is just a 30 nanometer PFO film spin coated on a piece of glass. So once we get this sample, the first thing will be doing some kind of XPS measurement to see is there any contamination on the surface. Then we do the high resonance scanning for the carbon C1sp to determine different kind of carbon binding energy. You can barely see some kind of pipeline transition down here, but it's not very obvious. So we'll go ahead and do some kind of REOS measurement to get a more obvious pipeline transition with different energy level. Then we'll go ahead and do some UPS measurement to get additional energy level for the HOMOs and hosts. So by taking all the data from all three spectrum, we can generate some kind of energy level diagram and to understand the electronic structure for this PF4 material, in addition for just chemical information from the XPS data. So that's why for such multi-technique tool, we can help to us to analyze the many different aspects of your sample. So that's everything I want to talk about today. Thank you for your attention. So if you have any question now, I'm happy to answer it now. If you wanted to have require any further discussion related to your sample, your experiment, or if you need any help to interpreting your XPS data, please feel free to contact me through the email shown on the screen here.